Today we are going to study transportation management, and in this lecture we're going to look at some important decisions that transportation managers make in their career, in their work life. And we want to look at, how can we make those decisions in an evidence-based way, in a way that can optimize our logistics costs, in a way that can be the best for our organization. At this point, you should have some basic knowledge of transportation, different modes, their advantages, strengths, things like that. And this information has been covered in a previous lecture. So let's get started. The first topic we're going to look at is intermodal transportation, because you might have learned about the different modes of transportation using truck or rail or water, barges on waterways, or ocean freight, or large ocean ships, air, pipeline. In many cases, you have to use trucks in combinations with the other mode, because rail, air, water barges, ocean freight, they're not door to door. They go from terminal to terminal, airport to airport, port to port. And so to connect them, we need to use trucks. And when you use two modes of transportation, it's called intermodal, meaning combining more or connecting or combining more than one mode. A lot of times in logistics, we use the term drayage to refer to using trucks to go from a warehouse or a distribution center to a rail terminal or an airport in the same city or close by. So when trucks are used for short trips to just connect, let's say, an airport to a nearby distribution center, we call that drayage. But sometimes we need intermodal without drayage, where the truck is going to take it from the New York port all the way to Chicago. That's a long haul truck trip. And that is called intermodal. Using drayage would also be intermodal because you're going from, air or rail to truck. So the reason intermodal is so popular is because it solves the accessibility problem of rail, water, and air by combining those options with truck. And so here you can see some intermodal combinations. So when we combine the rail by truck, some people call it piggyback because I guess rails are slow and that's part of the journey. And then with air, it can be called birdie back or air plus truck, and water plus truck, fishy back, or, water plus truck combination. Water includes barges as well as ocean freight. And then you could have pipeline with truck as well. When you go to fuel your car at a gas station, the fuel at the gas station has probably come to that point using pipeline and truck both. So it was probably pumped through a pipeline from some refinery, and then at a certain terminal or end point, it was pumped into a fuel tanker truck, which then drove to the gas station and fills up an underground tanker at the gas station. And then you pumped gas out of that underground tanker into your car. So all these combinations are very popular. In particular, we're going to look at what I've pointed to in red, which is combining water with rail or truck for moving stuff internationally, because when you move stuff internationally, you're sometimes doing air, but a lot of times you're doing ocean transportation. So if you have ocean freight, that's going to go to a port. And then from the port, you have usually multiple options, at least in the US. Some countries don't have a lot of rail networks, so they only have truck options. But in the US, you often have rail and truck both options, and you can use rail or truck to get it inland to distribution centers or factories or customer locations. Okay. So imagine Amazon distribution centers. If you're working for Amazon or Walmart, you'll be doing this a lot. You'll have a lot of goods coming in from overseas into ports in the United States, either East Coast ports like New York port or West Coast ports like the Los Angeles port. And then from those ports, you'll need to move them to distribution centers of Walmart or Amazon. And you'll have multiple options. We're going to look at, some of the decisions involved in that as well. Okay, so let's look at port to market. Okay, what this refers to is that part of the journey where you have goods arriving at ports and you need to move them to be accessible for sales either at distribution centers or retail stores or regional warehouse, things like that. So a large quantity of goods arrive at US ports in standardized containers on large container ships. 2024 statistics tell us that the inbound volume was the equivalent of 28.2 million TEUs. A TEU is a 20-foot equivalent, and we're going to look at 20-foot versus 40-foot containers shortly. So 28.2 million TEUs, 20-foot equivalents, that's roughly 77,000 TEUs per day. So that's a lot of volume of containers coming in. And a lot of this volume comes on the West Coast to ports of Los Angeles and Long Beach. And now the logistics challenge is, how do we move these goods to inland distribution centers, factories, and customers? So your inland distribution center could be in Illinois, it could be in Michigan, it could be in Texas, it could be far from the port. So this could be a significant journey. So as we think about that, we need to look at what are containers. Containers are these boxes which are used for international shipping. Before 1956, goods were loaded piece by piece into ships' cargo holds, like a big empty section of the ship. You would have people carry sacks of goods or boxes of goods into the ship and kind of stack them in the cargo hold. This was very costly and labor intensive because you have to pay so many people for so many hours to do that, and costly not just in terms of money but also time. It took a long time to load up a ship. And then when the ship arrived at the destination, the same process had to be repeated. The ship would have to be unloaded kind of piece by piece, took a long time. So a container, a standardized reusable metal box, was designed, and it was designed to have certain features. It's strong, it can withstand, being put on top of it, it can be stacked. While these containers are being transported across oceans, they have to be waterproof because they could be spray from the ocean, rain, and they can be locked and sealed so that when you get at the destination, the seal is intact, you're sure nobody messed with your goods. And what these containers allow, they have a standardized size, a maximum weight limit, and the corners are standardized, what size, what shape they're going to be, which allows for equipment to kind of pick them up. So there are cranes, specially designed cranes, that can pick up a whole container, move it to the dock, or take a container from a dock, move it onto the ship. And so now loading a ship with thousands of containers is really fast, much faster than it used to be before the containers were invented and put into operation. And so almost all international cargo, in air they use different boxes or different type of containers that can fit in the belly of the aircraft. So that's different. But for the ocean transportation, international transportation, almost everything is going to go inside containers. They can also be stacked very high on ships. So there's reinforced steel along the edges, like these columns, or at the corners. And so they can support weight. And so you can stack them, several containers on top of each other on ships. And they don't get damaged and they don't damage the goods inside. So containers come in different kind of versions. This is like the red container you see here is like a standard container. And this is showing you how things can be inside. So you can see goods are stacked in a container. Now notice something very interesting. You can count the number of boxes stacked vertically inside this container. So you can say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The manufacturer of this product, they would design the packaging so that a whole number of boxes can be stacked up high. Imagine if each box was a little bit larger and then you had some space left over at the top, but it was not enough to put another box. You'd have that space would be wasted in the container. And so if you have, packaging that wastes space in a container, you can redesign it and kind of design your product to be packaged in a certain way so that you use up all the space in a container. Otherwise, you'll be paying for just shipping empty air. And so that's one thing that often logistics does in collaboration with manufacturing, is to make sure that the packaging or the carton size in which your products will be packaged, which can be an outer packaging, because you could have an inner packaging of the actual product, and then you put maybe 20 of your products into a bigger carton. This outer carton needs to be designed in a certain way that it fits nicely in a container, not just vertically, but also on the other dimension. So you can put as many as possible inside a container and not have wasted space. You can also get containers that maintain their temperature. So they usually have a generator running on fuel, which runs a refrigeration cooling unit. And so these can be used to ship things like milk products, ice cream, certain medication, anything that needs a certain temperature to be maintained during the journey. These are called reefers. And so you can get these. Obviously, some of the space is used up because you can't make the container bigger, standardized size. So some of the space is used up by the refrigeration unit, but you do get this temperature controlled container as well. Now, containers can be shaped like tanks to carry liquids. Okay, and why do we need tanks, and why can't we just put liquid in this rectangular box? I think it has something to do with cleaning the tank, that this particular shape allows the tank to be cleaned more in a better way when you have to reload the tank with a new product or avoid contamination, things like that. However, the tank can't be just the tank. You have to put this blue structure around it because the container dimensions and the corners are standardized. So you still have to have all the corners exactly like you would on a container, like a box container. And you have to have the same dimensions, like the same distances between the corners. But then the middle can be this other shape. Now, container handling at ports, you can see this big crane. And you can see it's moving and loading a ship with containers. Look how many containers are stacked up on this ship. These are huge ships on which are loaded at ports, and you can move these containers, very efficiently with these big cranes. Now, the operation at ports has become very capital intensive. It's very expensive now to make a port with these huge cranes. But the variable cost is very low. The cost to load a container on the ship, it doesn't take that long, and it's just the cost of energy of running these machines. It's not that costly to load and offload ships now. And what that means is that the investment in the port pays for itself, because if you charge a little bit more than variable cost, you make some money to pay for the port. Because the port operation is variable cost is low, you don't have to charge too much, so people will use your port, and a lot of volume flows through the port, you will be able to recoup your investment in this infrastructure. Then you have these special equipment in the port yard, where the containers may be stacked up here waiting for a ship, because ships sail on certain schedules. So if these containers arrive, let's say a couple of days early, they'll be stacked up here in the yard, and they can be moved to the ship. Similarly, on the receiving end, a ship may be unloaded onto the yard and then maybe loaded onto rail or truck using equipment like this. Again, another example of equipment at ports. And this is an example of that big crane that offloads a ship. It's putting containers directly onto trucks. And these trucks will either take the container all the way to the next destination, like a distribution center, or they'll go to a transloading center close by, which will just be a drayage move, like a local move. And at the transloading center, they'll open the container and move the cartons out onto rail or truck or whatever else they need to do, and then return the container. Because these international shipping companies, they want their containers back. Container is reusable. You don't just use it once and throw it away. It's very expensive to create, made of metal. And so if you don't return the container within a certain number of days, you may be charged per day for keeping the container longer than you're allowed to. And so that's where the transloading center can come in, where you're going to you quickly go to the transloading center, empty the container, and return the container to the port so that you're not charged a fee for keeping the container too long. So the advantages of container, they drastically reduce cost of shipping. So international freight movements became a lot more cost effective because the port operations now are a lot more cost effective. Also faster. Instead of taking many, many days to load up a ship, now a ship may be loaded up in 1 day or 2 days. So speed of turnaround at ports leads to time savings. Safety reduces damage, airtight, can be airtight. The containers are usually airtight. If you have something that needs some ventilation, that can be built into the container to have like a filter and some portal to bring in air, but usually they're just gonna airtight, waterproof, can be locked and sealed. So reduces theft, reduces damage, keep goods safe. They can be stacked on top of ships, so ships can be utilized very effectively. You don't have wasted space on the ship. You can ship many different types of things in containers because there are refrigerated containers available. And then the International Standards Organization, ISO, has standardized different containers so that, a container produced in Europe will work in the ports in the US and China and South Korea and Japan and India. So you could create a container anywhere in the world, make it, and then you could send it anywhere in the world because everything has to meet the ISO standards and all the equipment is designed around these ISO standards. So the 4 commonly used containers, and there are others, but these are the most commonly used ones for the ISO standard containers, are 20 feet standard, that's called the TEU, 20 feet equivalent unit. So we often measure volume of ships or ports in that. So that is 20 feet by 8 feet by 8 feet and 6 inches, which is 8.5 feet. These are the dimensions. The tier weight is the weight of the box, the weight of the container itself. That's 5,000 pounds. Okay. And then because the total weight has to be 67,200 pounds, according to the ISO standard, you subtract the tier weight of 5,000 from 67,200 pounds, and you get the maximum payload weight of 62,200 pounds. This is for the container and for container handling at ports. However, when you put this container on a truck, the truck has to obey laws of the roads and other regulation in the country, and often trucks are not allowed to carry such a high payload. And we'll talk about that. So even though the container ISO standard allows you to put 62,000 pounds in a 20-foot container, if you have something very dense, like very heavy equipment or something, you may not be able to do that because at the end of the day, you have to move the container onto a truck, and that truck has weight limits too. Because of the road, if the trucks are too heavy, they damage the roads. However, in certain situations, certain ports will have a permit to move heavier containers than what the roads allow on like a special road to a transloading facility where the container can be offloaded and moved to trucks or rail or other things. So sometimes you can ship, containers that are heavier than what a truck can carry, and then have them processed near the port at a special facility and then moved on to some other mode of transportation. So that doesn't mean that you're limited always by the truck weight limit, but often you are. And also in some jurisdictions, you may be able to pay a permit fee for a container to move a heavier container, and then governments will use that permit fee as revenue to fix the roads that get damaged when you move heavier containers on those roads. And then there's the cubic capacity, how much space you have inside. Okay. Then we have a 20 feet high cube container, and the only difference is that one of the dimensions is 1 foot more. The height is 1 foot taller than the regular 20 foot. And what that gives you is making it 1 foot taller adds very little amount to the weight of the box. The box only weighs 100 more pounds, but it gives you a lot more cubic feet. Notice you went from 1172 to 1312 cubic feet. So it gives you a lot more cubic feet. Okay. And a lot of people like that because oftentimes you're going to cube out before you weigh out. So these two terms are really important in logistics. What is cube out and what is weigh out? Whenever you're loading something, truck or a container or a rail car, all of these things, there's a weight limit and a volume limit. Obviously, a rail car or a truck or a container, they have limited volume, they have dimensions. You can't put more stuff in when they're full. So that's the cube limit. Volume limit is called a cube limit because volume is measured in cubic something, cubic meter, cubic centimeter, cubic feet, right? The measures of volume are something to the power 3 or cubes. So the cubic limit is the volume limit. So if you're loading up something that's not very heavy, you'll fill up your truck or container before you hit the weight limit. So imagine you put a whole bunch of pillows or blankets in a truck. The truck will get full well before you hit the weight limit because these things are not heavy, but they use up a lot of space. They're like bulky, they use up bulk space, but they're not very heavy. Now imagine you put like weights, the weightlifting weights like plates, weight plates or something like that, or just blocks of metal, like heavy density metal, or like let's say uranium, which is very high density, some high density metal blocks of that in a truck. You may weigh out before you cube out, which means you may hit the weight limit. The truck still has some empty space, but you can't put in more bars of heavy metal in it because the weight limit has been reached. You can't add more weight. So that's called weighing out. You hit the weight limit before you hit the volume limit. Now, most things that are shipped like clothes, apparel, toys, electronics, they're not that heavy and dense. And so most of the time you're hitting the cube limit before you hit the weight limit, which is why having extra cubes by this high cube container can be very useful because you can ship more stuff but just using up a tiny 1 foot more of vertical space. And vertical space is not a problem because ships are stacking these on top of each other. And you can, if each container is 1 cube taller, you stack 10 containers on top of each other. That's just 10 foot more of vertical space. And, vertical space is not an issue because you're stacking them on top of ships. And so that's an easy, low-cost way to add cubes to container, the high cube container, which is why the most commonly used container for international shipping is the 40 feet high cube, which is 40 feet by 8 feet by 9.5 feet. The box itself weighs 8,700 pounds. You can maximum cargo weight based on the ISO limit is 58,500 pounds, but you may not load up that many pounds in it because you may hit the cube limit first, or because of the truck weight limits, because it's going to go on a truck eventually, or on rail and things like that. So there could be other limits and other parts of the journey involved. Okay, so this is very common to ship electronics, consumer goods, from one continent or one country to the other. And I've specified the ISO standard where I got these values from. And you can, if the standards change in future, you can just look up what the values are. Usually the shipping company you're hiring, they'll be able to tell you the containers because when you hire a transportation service, often they provide the container. And then if you use it for more days than they specify, then you pay a rental fee on it. But the container is something not that as a shipper or a purchaser, importer, you don't have to purchase your own containers. Like when you buy a transportation service, like a shipping service from one port to the other, the container is often part of that package. Let's look at a couple of examples. So let's say you want to ship some heavy, dense stuff. So industrial steel boards, stones, tiles, heavy machinery, dense liquids. Then the 20-foot container might be the best choice because you'll hit the weight limit long before the box is full using a 40-foot container. If you look at this slide, the weight limit is actually lower on a 40-foot container. Why? Because the total weight limit is the same, 67,200 pounds, but a 40-feet box, the box itself weighs more. So there's less weight left for the cargo. Same thing, if you're going to put it on top of a truck, and let's say on the truck, you can put a maximum 45,000 pounds because the trailer plus truck combo has to be 80,000 pounds according to the US regulations. So let's say you can put a 45,000 pound container on the truck. If the box itself weighs more, then you have less weight limit left for what's going to be inside. So if you were to ship these, tiles or stones or steel bolts in a 40-foot high cube, that's going to be a waste of space because you're going to hit the weight limit well before the container is full, and you'll be paying for shipping empty air. So you want to use a smaller container. Okay. But let's say you're shipping consumer electronics, toys, apparel, furniture. These are not very dense. They take up a lot of space but don't use up a lot of weight. Then you want to use the big container, the 40-foot high cube one. You'll need every inch of cube space because you'll fill the box to the ceiling and still be well under the weight limit. You're going to cube out a lot before you weigh out, and so you want the more cubes, the more volume. Okay, so depending on what you're shipping, you can decide which container is better for you. 40-foot high cube is the most commonly used container because most of the stuff that's shipped, is not as dense as stones and tiles, and it needs, a lot of volume, but doesn't hit the weight limit. Now, there are non-standard containers as well, but when they do stack them up, you should notice that at the very bottom layer, I have two 20-foot containers. On top of that, I have the 40-foot container. So along these corners on the sides, the rightmost side and the leftmost side, that's where the weight supporting beams are. So all the weight is flowing down along those two bottom red arrows, along that vertical. So when you go to a 45-foot container, which is part of the ISO standard, it gives you about 2.5 foot extra space on each side. The 2.5 foot extra overhang, still you have to put the vertical column that's going to support the weight at the 40-foot mark. So if you see, there's a vertical line here, which is right on top of the gray 40-foot container, and that is where the weight of the container is going to be supported. Okay. And then if you go to non-standard containers, again, you have to put, you can see very clearly in the white laser box that there's a vertical beam or column at the 40-foot mark, which is where the weight will be supported. And then the extensions of 4 foot on each side to get to 48 feet, they are there, but the weight is going to be supported at the 40-foot marks, right on top of a 40-foot container. Now, why do 53 feet non-standard containers exist? Because if you look at the US, a truck trailer combination, and we'll talk more about this in a little bit, the trailer can be 53 feet long in the US. So if I put a 40-foot container on a chassis, like on the trailer bed of a truck in the US, then I have a lot of space wasted because my truck, the trailer part of the truck can be 53 feet long. So if you want to move stuff within the US and you want to use containers and put them on top of a chassis like a truck trailer bed and then hitch them to a truck and kind of move them along the US, you want to use 53 feet containers within the US. So what happens is that a lot of these big companies that move a lot of stuff within the US, like Amazon and Walmart, they need to use 53 feet containers within the US mainland. So what they'll do is if the factory producing the 53 feet containers is, let's say, in Korea or Japan or somewhere else in the world, they don't want to buy those containers and ship them to the US empty. That's just wasted transportation money. You're paying so much to transport these empty containers. So they'll put their goods inside them that they're importing, and certain ships and carriers will, given certain amount of money, will ship these non-standard containers because they can rest them on top of a 40-foot because of the weight support beams are at the right points. And so certain shipping carriers will allow you to ship a 53-foot container from Asia to USA, for example. And then you can produce these in Asia where the factory is producing them. You can fill them up with your product, bring them to the US, and because you own the container, you get to keep it, and now you can use it on your trucks in the US to move goods around within the US between your distribution centers and things like that. Okay, so let's talk about the US road weight limits, because that's very important, because what we are trying to build towards is, remember, a port to the inland transportation. If we have stuff coming at the ports, how do we get that stuff to our distribution centers? That's what we are kind of talking about right now. And so part of that is that the stuff is going to go on roads, on trucks, right? So what is the US road weight limit? So US Department of Transportation generally limits the total weight of a truck plus trailer plus the fuel in the truck plus the driver's weight, everything combined, to 80,000 pounds. Okay. And then there's also a weight limit per axle. An axle is what connects wheels. So if you look at the trailer, when you have multiple wheels together, that's called a tandem axle. So if you look at a trailer, towards the back, you'll see like two like rows or two sets of wheels close to each other, because each set of wheels is going to have the axle going from right to left. So for that, the weight that's being supported by that tandem axle can be 34,000 pounds. And then in the front, if you have a single axle, that has to be 20,000 pounds. Now, the tractor part or the truck part, which is the engine of the truck and the cabin where the driver sits, can weigh from 15,000 to 25,000 pounds. And then the 53 feet drive and trailer weighs from 10,000 to 15,000 pounds. Combined total, they weigh about 35,000 pounds. So how much can you put inside the truck is about 44 to 45,000 pounds. Okay, a lot of shippers will put in about 44,000 pounds, because if you go above, if you get very near the 80,000 pounds, you get in the illegal fine territory. And based on the fuel in the truck and the weight of the driver and their stuff, you don't want to get too close to the limit. Especially, the scale may have a certain accuracy as well and things like that. Now, if your truck has a battery pack or some sort of scrubber to reduce emissions, these things can have their own weight, and that can reduce your payload that you can load as well. So at the end of the day, total everything, driver, fuel, everything else, total has to be 80,000 pounds. And you subtract everything except the cargo, and that gives you how much cargo you can put from 80,000 pounds. So usually you can go for like 44,000 pounds on US trucks. So if you're shipping, these containers and you're going to put them on a truck. Now you may offload containers and load up trucks in a transloading facility, but if you're going to put these on a truck from the port, then you need to make sure that you don't put like 60,000, 58,000 pounds of stuff in a container, because you can't load that onto one truck. At least you'll have to split it up into multiple trucks. But if you're going to put the whole container on a truck, you wouldn't be able to do that if the container and what's inside it is weighing more than what the truck will allow. So now the problem is, when you have these containers come in, they're over-engineered for land travel. They're designed to be put on ships and be stacked on top of each other, so they're very heavy. The box itself, the container box, is very heavy, and it's very strong. But you don't need it to be so strong and heavy to move on the roads, because you're not going to stack them up as high on trains or trucks as you would on the ships. For domestic shipping, 53 feet trailers or containers are preferred, as they're larger than ISO containers, so they take advantage of US highway regulations. A 53 feet domestic trailer has 60% more internal volume than a standard 40-foot high cube, even way more than the high cube one. And most consumer goods cube out before they hit the weight limit. And so that means that, it's more efficient to ship to do the land part of the journey in 53-foot dry van trailers or 53 feet containers. Also, shipping lines want their 40-foot containers back at the port so they can be sent back with other stuff in them, or just sent back to be used again. And so you can't just use the containers to move around on the mainland for many, many days. You need to return those or pay a per day fee. Okay. So that is why we have, certain options. We can either go to transloading and then empty the container, return the container, and then, fill up our truck. Or we can pay for the rental of the container and use rail, intermodal rail, and things like that. So let's look at what is transloading. Transloading is moving cargo from ISO containers to truck plus trailers, so into the trailers, or into domestic 53-foot containers. Okay. So often what transloading process works in 3 steps. The first step is drayage. A short haul truck pulls the 40-foot container into a specialized facility very near the port. Then the strip part happens, where workers unload the floor-laden boxes from the ocean container, and they stuff those boxes, and sometimes they're resorted because a certain amount of boxes may be going east towards Texas from California. A certain number of boxes may need to go north towards Washington State or Oregon, things like that. So when you offload from the containers, you may be like sorting them into different trucks as well. You stuff up the trucks. And then there's the 3-for-2 rule, because, if you're going from 40-foot containers to 53 feet dry vans, the trailer behind the truck, or 53 feet domestic containers, then often 3 40-foot containers will fit into 2 domestic trailers or 53 feet domestic containers. So you'll often go from 3 to 2. So 2 trucks will carry the goods that were in 3 containers that came in from the ocean. Okay. So here are the popular options we have. So ocean freight comes in, okay, and let's say the US port of entry, like LA, Long Beach. Now you have what this option called inland point intermodal, direct IPI, direct inland point intermodal. What it means is you can just put the container directly onto a rail, onto a train. And often these trains will stack them too high. So they'll not be just one layer of containers, it'll be like another container stacked on top of these. And then this rail will go to the closest city to where you want to be. And then from that terminal, okay, you will have trucks pick up the containers and bring them to your distribution center, where you'll offload them and return the empty containers back to rail. And then the rail will have to move the empty containers back to the port. So moving empty containers back is also sometimes required, because obviously if the train terminal needs to use these containers to ship product, like for international shipping, they'll use those containers. Other companies will load up their stuff in those empty containers and move them from the rail to the port, and then the port out of the country. But sometimes you have more empty containers and less demand for shipping stuff out. And then sometimes you have to put the empty containers back and move them to the ships, or at least to the port. So that's one option. That's called direct inland point intermodal. You go from port to rail. Not every single port has this option, but some ports do. Then the other option is what we talked about, transloading. You do drayage. You have trucks carry these containers to a transloading facility where you offload and load onto trucks with their 53 feet dry van. So this white box behind the truck, that's a 53 feet dry van. Or it could be a 53 feet domestic container, just fits on top of a chassis. And then the truck drives it door to door. There's no need to move to another truck. Just truck will drive door to the door of your destination, your distribution center. Now the third option is that you can also put these containers on a truck, just like put them on the rail, and do truck intermodal. But that's not that popular, because a truck can carry a 53 feet domestic container. Why would you put on a smaller container on a truck and then have the truck drive the container? So you're wasting space in the truck. The truck could have carried a bigger domestic container or a dry van, and then you're also paying the per day rate for container because you're not returning it quickly to the port. And so mostly the options are inland point intermodal on the rail, and then at the last stage you use a truck to go from the railway terminal to your distribution center, or you do drayage to transloading facility. From transloading, you put them on trucks that'll go to the door of your destination. Let's look at an example comparing these options. So let's say 3 40-foot standard containers arrive, and the 3 containers together contain 3,000 units of electronics item, let's say a PlayStation. So each container has 1,000 PlayStations inside it. We need to move them to the company's distribution center in Chicago. So here are the options we're going to compare. Okay. We can do direct IPI, where containers are loaded directly onto rail from the port, and the rail takes them to Chicago terminal. From the terminal, the trucks will take them to a DC. These will be containers, directly 40-foot containers will be moved to Chicago to a DC, and then they will be returned to the rail, the rail company that moved them. And then the rail company will either fill them up with goods and move them to the port, or they'll move empty ones to the port. It's up to them what to do with them. And then the other option, second option, is transload the 3 containers into 53 feet truck trailers and drive to the DC in Chicago. And then the last option is that we transload the 3 containers into 53 feet local containers that are sent on rail to the Chicago terminal and from there to on trucks to DC. So that's transloading combined with rail. That's the third option. And the second option is transloading done with trucks. Okay, so this is an example. You can find the costs for each option through the the transportation companies that provide these services. The reason I'm providing this example is to give you a certain idea of the some of the costs that can be involved, because it's not just the main line freight. That's the middle row in the table, main line freight, which is the biggest expense. That is the expense of moving the containers or the 53 feet dry vans or domestic containers, the journey from California to Chicago. But there's many other costs involved. In option 2 and 3, we have to pay the drayage from port to the transloading warehouse. Okay, so because the port can't load them directly onto trucks, because we're not going to use those 40-foot containers that came in. We're going to use 53 feet dry vans or domestic containers. And 3 40-foot containers are going to go into 2 53 feet dry vans or domestic containers. So in options 2 and 3, we pay for the drayage from the port to a transloading warehouse. Then the transloading warehouse will charge us labor fees to offload those containers and load up the trucks or the 53-foot domestic containers. Then you'll have the main line freight, which is the freight from California to Chicago, and rail is going to be cheaper than truck. And you can see that the direct IPI rail is more expensive than standard rail, because they provide you this service where they pick up from the port and it moves on the same waybill, the same documentation, and so it's a little bit more convenient and it's more expensive. Then at the destination, you can have drayage with option 1 and option 3, because the rail terminal is not where your warehouse is. You have to move it from the train terminal to your warehouse and pay a trucking company to do that. And so in option 1, you're moving 3 containers with 700 times 3. In option 3, you're moving only 2 53 feet domestic containers with 700 times 2. Okay. And then in option 1, when you, the minute you move the container, the rail company will put the container on a chassis, like this flat bed with wheels, so that can be hooked to a truck and driven. So the chassis and the container, you're going to have to pay a rental fee for them. They may give you a couple of days free, like 2 days free. If you don't rent 2 days or 3 days, then it's this much charge per day. But you might end up paying a charge per day, and that depends on how long you take to offload them in the warehouse and return those things. In option 2 and 3, the transportation company is going to deliver to your door, and so in their own truck, and so you're not really borrowing the chassis or the container from the shipping line or the train or the railway company, and so there's no fee for that. And so these are, you have to just keep in mind that there are all these sorts of fees that could be involved, or different types of cost in comparing these options. And don't just look at the mainline freight only. Oh, it costs this money per container, and that's how I compare the options. You have to think of every step of the process, add up all the cost, add up all the time, and then compare. So in the end result, our transportation service comparison is 15,300 direct IPI. It takes 14 days. And then the transload to rail domestic take 11 days. Why is direct IPI taking long? It could take shorter too. It's just an example. It could take shorter too, but the reason it's taking longer here is presumably because direct IPI has limited capacity and the capacity is booked up, and so you don't get the first maybe rail out of the port. You maybe have wait a couple of days at the port or 3 days at the port before you get the direct IPI train. Okay, so this is fairly standard work you might do as a transportation logistics manager, compare different options on time and money and kind of make your decision. But this is just the transportation part of the cost. Because the transit time is different, that affects your lead time and affects your inventory costs as well. And we're going to look at an example of different transportation options with different costs and time. And we'll bring in the inventory costs and see how to make the optimal decision shortly. But from just the transportation cost perspective, you can compare options on the cost and the days. And rail is obviously much lower than truck. So remember that the faster option, the truck, has additional inventory savings. So, just the pipeline inventory costs can be significant if you're, or let's say, this 1.5 million worth of inventory in those 3 containers of PlayStations, because it's like $500 a piece times 3,000 pieces. And, even if your cost of capital is just 10%, the pipeline inventory cost alone would be $410 per day. So for high value items, faster options, even though they're more expensive on transportation costs, can often make sense because they save you on inventory costs so much. You don't want your capital tied up in inventory for days on end on the journey. But for cheaper goods, where the inventory costs are not as significant, the cheaper transportation option can make more sense. Okay, let's look at an example where we look at different transportation options and look at the full impact on transportation and inventory costs. So let's say we're a computer store and we sell about 700,000 units of USB keyboards annually in a year. You could be a retail chain, with multiple stores in the city. You could be an online business. A keyboard costs $30 to purchase from the supplier. So let's say we have an overseas supplier. Or I think in this case we just have a supplier which has a warehouse in the country, so we're just moving from that warehouse to our location. A lost sale results in $15 of gross margin lost. Inventory carrying costs are 30%. Our retail store is open 312 days a year. So daily demand is 2243.6 units. That's just the 700,000 divided by 312. Standard deviation of daily demand is 500. We have 3 options to transport keyboards from the supplier's distribution center, and the fixed ordering cost is $50. So we'll use a cycle service level of 95%. Which option should be used to minimize the total cost, which is transportation and inventory costs combined? And we have these transportation options with different rates. So air, we could transport by air. It's the most expensive. It's going to cost us $1.4 per keyboard per unit of product. And the door-to-door transit time is 2 days. The lot size depends on kind of like the how many will fit in, the truck or the rail car or the box that's shipped with air. Now, you could have any order size or lot size you want, but then you would be shipping partial containers or partial rail cars, partial truckloads, and these rates only apply if you ship this particular lot size, because you know that a truckload will have a certain cost, and then you divide that cost by how many keyboards fit in the truck, and you get the rate per unit. So if you're not shipping a whole truck, that rate per unit doesn't apply, because then you have the LTL shipment rate. So if you look at the previous example that we did here, when you have the total cost 15,300 or 16,300 or 12,100, we know this is the total cost to ship 3,000 units. So if you divide this number by 3,000, you'll get about $4 for option 3 or $5.5 for option 2. That is the cost transportation rate per unit. So basically what we are doing here is we have looked at the total transportation cost to ship like a truckload or a rail car, full rail car or something like that. And we've added up all the transportation expenses, and whatever total we got, we divided that by the how many keyboards we're shipping in that truckload or rail car or something like that, right? And that's our lot size. Okay. Because for that lot size, this transportation rate applies. If you change the lot size, then you have to figure out what transportation rate would it be. So we have door-to-door transit time and we have sanitation of transit time. Note there's no supplier processing time here. So when we order the supplier, he's ready to load up because he has finished goods inventory in the warehouse. He's ready to load up the truck and ship stuff out. okay, to take the truck to the airplane or rail terminal, or the truck, if you're going by the second option, the truck just drives to your warehouse. Okay, so we know that we are going to calculate our total inventory cost using this long formula. This was covered in a previous lecture. You also have an Excel template that does this. Remember that Q is the lot size in this formula. And so if you use the Excel template that was provided, then the Q may be being calculated using the EOQ formula in that template. So you have to change that and put in Q as the lot size given in the question. Now, a lot of this inventory calculation is going to need to know this standard deviation of demand during lead time, SDL, to calculate the safety stock. And so we do that first, and then we apply this formula. Okay. So SDL is given by lead times times standard deviation of demand squared plus demand squared times standard deviation of lead time squared, the whole thing square root. Okay, so for all of these options, we can put in the lead time, which is basically just the transit time, because there's no supplier processing time. Lead time is supplier processing time plus transit time, because supplier processing time we're assuming is 0. Just the transit time, door-to-door transit time is our lead time. And then the standard deviation of demand is given as 500 per day. And then the standard deviation of lead time is given here. Of the transit time, this is standard deviation of lead time, because the transit time is the lead time in this case. And that is SL is also given. So we can put in this formula, calculate standard deviation of demand during lead time. Okay. And then we can also calculate the average inventory level in our warehouse given the option we'll use, because that's based on the lot size over 2 plus Z times SDL. This part is the safety stock. Okay. And so we can do all this calculation, and then this will make our total cost calculation very easy. Again, I'm not going to go over the exact fine details of the calculation, because this sort of calculation has been covered in a previous lecture, and you should review that if you don't understand something about how to do this. But I'm showing you all the steps. Okay, so when we Q over 2 plus Z times SDL, this part in brackets here is the average inventory level. So when you multiply by H times C times the average inventory level, you get the carrying cost, which is given right here, inventory carrying cost in the middle of the table, okay, for the 3 options. Now, remember that C is not going to be $30, because $30 is what you pay the supplier. The landed cost C is going to be $30 you pay the supplier plus the transportation rate, and that's R is going to change with each option. So for truck, R will be $0.2, but with air, R will be $1.4. So you'll get C will be different for the different options. Okay. So, and the average inventory level is different for the different options. So when we plug the average inventory level for the different options, multiply by the landed cost, which is again different for the different options, times H, which is 30% or 0.3. We get the carrying cost. Similarly, we calculate the ordering cost, out of stock cost. K is going to be $15 because we lose $15 for our lost sales. K is cost of lost sales. EZ, the formula is given in the Excel template, and it's also given, the EZ value is also given here. For CSL of 95%, EZ is this value. If your CSL cycle service is different, then you get a different EZ. Again, the formula is given in the Excel template on how to calculate EZ. It's called the unit loss integral. And then the pipeline inventory cost, again, this is a very common mistake. Students put C here. You don't multiply by the landed cost here. You multiply by the cost you pay the supplier, because while the inventory is in transit, you haven't paid for transportation yet. So the value of your inventory is C naught, the value you pay the supplier, not the landed cost. So we can compare the options. And if you look at the different options, you get a total cost, which is the transportation cost. That's just R times D, the transportation rate given here, times the annual demand, because in a year you'll move that many units through that transportation mode. So 700,000 times 0.12 is transportation cost of piggy bank. 700,000 times 0.12, is transportation cost of piggy bank. 700,000 times $0.2 is transportation cost with the truck. For this annual transportation cost, all these costs are annual costs. Okay. So over 1 year of working with this supplier and piggy bank transportation mode, we will spend $768,185 on inventory and transportation combined. For a truck, notice the transportation cost is close to double than using rail. with truck, piggy bank. But you save so much on inventory carrying cost with a truck because your lot size is smaller, your lead time is smaller, your safety stocks are less. So notice the big savings in inventory carrying cost that leads to truck coming out to be cheaper even though truck is more expensive on transportation. And then air, your inventory costs are really low. Okay, because you're shipping these small batches, because the air uses smaller containers or smaller boxes to ship product, and you can book a whole box each time. But then look at your transportation cost that's just so high that the inventory savings are not enough to make air competitive. Air is the most expensive. Yeah. So remember, if you have just looked at the transportation rate, you would have said, oh, rail is the cheapest. I'm going to do piggy bank, rail plus truck. That's so much cheaper than everything else. But when you factor in the inventory cost, you figured out because that in this example, the truck came out to be the cheapest. So it's very important because you have the transportation and inventory cost trade-off to look at the impact on inventory cost when you make transportation decisions. Now, obviously, if you're shipping something only once and you're going to never ship it again, then there's no safety stock involved. Then it's just the pipeline inventory cost and transportation cost. Okay. Let's say you're buying some unique item for this Christmas season. You're never going to sell it after this season. And it's just a one-time thing. And so you don't need to order again and again. It's just going to place one order. So there's no point of annual ordering cost because you're only going to place one order ever in the whole lifetime of your business. And then, the stock out cost is going to be the same for all options because you're going to place the order for the same amount of quantity. Because no matter which option you go, you need that amount of quantity. And so then you just care about pipeline inventory cost and transportation cost for a one-time order where there's no repeat order. But that's a very rare situation. In most situations, you're ordering items again and again over the year. You're replenishing that item. So if you're going to be running with that SKU or item for the whole year, then you want to find the annual inventory cost and the annual transportation cost using this method that I showed you that was also covered in a previous lecture, and then compare them on total cost. Okay, now that we have looked at two things, one, we looked at an example which was port to inland. Okay, do we go by inner point intermodal, or we do a transloading facility to rail or truck, and we just look at the transportation cost there, but obviously you can also calculate the impact on inventory cost. Then we looked at an example of 3 different transportation options with air or piggyback with rail and truck for keyboards, moving them from a supplier's facility to our facility, and looked at the total annual cost. Now we're going to look at, international shipping. So these long routes, bringing something from outside the country. And we're going to look at, okay, how do we evaluate these different routes? And obviously, when you pick a route, these different routes take different amounts of time. There's also an impact on inventory cost. And again, whenever the lead time changes, you can calculate the impact on inventory cost using the formulas I've shared, using the Excel template that's been given to you. But let me just show you how you can look at the different routes by going through an example and then kind of figure out, okay, what is the risk with each route, what is the total time taken in each route, and things like that. So let's say we need to transport something. We are getting something that is produced in China, in Shenzhen, okay? And from Shenzhen, we need those goods moved to our national distribution center in Kansas City, okay? Kind of like in the middle of the U.S. somewhere. Well, a little bit to the East Coast side, but kind of like in the middle of the U.S., okay? Now, in this trip, we're going to look at it as 3 parts. First, we have the inland origin journey, which is going to be from the door of the factory of the supplier to the port in China. And then the second leg of the journey is going to be over water, port to some port in the U.S. Okay, and then we're going to go from the port in the U.S. to our warehouse, which is the inland destination part of the journey. So you will often be breaking up international shipments into 3 parts like that because the inland origin options are going to be different than the port-to-port ocean freight options, and then they're going to be different than the inland destination options. And so you have to look at each leg of the journey and find which option works there and kind of connect them to build your full transportation route and the options that are available for you. Okay. Now, I did draw a straight line here from Shenzhen to Kansas City, but that's not the shortest route because the Earth is kind of spherical, and so on a two-dimensional map, a straight line doesn't give you the shortest route. You have to look at a 3D representation of Earth and use a string to connect 2 points and see which kind of arc gives you the shortest amount of string. And often those shortest routes on the three-dimensional Earth are become like curves on a two-dimensional plot. That is why flight paths look curved when you look on a two-dimensional map. I just want to put it out there, in case there's some flat earther trying to be in logistics. Your logistics may not be the best career for you if you believe the Earth is flat still in this time and age. So the Earth is not flat, and the shortest distance between 2 points is not a straight line on a two-dimensional map. You have to find it using math or using a globe spherical representation of the Earth. Okay, so let's look at our options. So in Shenzhen, from Shenzhen, we have 2 ports close by. We can go to the Hong Kong port, or we can go to the Yantian port. And these distances are not very big. We can get to the port pretty quickly. So that's the inland transportation origin. And obviously, you can just use like trucks to get your stuff to the ports. And because the distance is so short, you can just, have containers packed at your supplies facility and have containers driven by trucks here. Because the journey is so short, you don't need it. It'll be more costly to pack them into other types of trucks and move them to the port and then transload them into containers at the port and then load them on the ship. You just want to make the containers at the supplier's facility because the supplier is so close to the ports, and just send the full container ready to be going on the ship onto these 2 ports. That's the first stage of our journey. Then the second stage is port to port. So one option we have is the CSCL America Loop, America South Loop, okay, which can start at Hong Kong or Yantian. It's the green line actually. I think it starts at Yantian. The purple line goes to Hong Kong. This is the green. The green is westbound. The pink one is eastbound. Right, so we are going eastbound, so we'll be taking the pink line, okay, and so we'll be going this route. We'll be hitting multiple ports to pick up containers, and then going all the way to the Los Angeles port on the west coast. Another option we have is this other transportation line, the APX Atlantic Pacific Express, which actually goes through the Panama Canal to the East Coast ports. So if we want to hit the East Coast port, because Kansas City is close to the East Coast, we can go with APX, but if you want to hit the West Coast port, we can go with CSCL. So depending on which shipping line we go with, which ports we get, we have that option. Okay, so for the last stage of our journey, and if we land on Los Angeles or Long Beach ports, we can move from there to the distribution center in Kansas City, or if you land on the East Coast port of New York, we can move from there. So to identify all of these options, you have to work with transportation service providers, and lay out all the options on the table. So I'm not saying these are the only options, but these are some of the options as an example. So we could do intermodal rail from New York Port to Kansas City. And we have the companies that offer that service. We could do truck, okay, for the last leg of the journey. So these are just the options listed out. For the first stage, inland origin, Shenzhen to ports, I can go to the Yantian port or the Hong Kong port. Now this time listed here, 2 days and 5 days, it doesn't take that long to go from Shenzhen to Yantian. The time listed here actually is kind of based on the ship schedule, because the ship may sail every 2-3 days or something. So on average, it takes 2 days, because the distance is so short that I can just move the container when the ship is being loaded. I don't have to move the container early and then wait on the port for 2 days. So, if I order from the supplier today or the goods are ready today, the supplier may just ship them after 2 days, because it's cheaper probably to hold the goods at the supplier's warehouse than to pay for a container being stored in the port for 2 days waiting for the ship. So, in this example, this time here is mostly based on the schedule of the ships at the port. But if it was more inland, the supplier, then you would have a time to go to the port, and then you may have a time of waiting at the port as well. Then port to port, from Yantian, we have an option of LA, $1,100 per container, 20 days. Or we can go from Hong Kong to LA in 13 days, $1,025 per container. And then we can go from Hong Kong to New York, which goes through the Panama Canal. It's like a more longer route, so it costs more, $1,200, and takes more, 29 days. Then at the US ports, there's different time to process the container and have it ready. So LA port takes longer, more congested. New York port takes a little bit less. And then in this example, so you have to check, like, the port's operations improve, things change. So you have to check the exact numbers when you are doing it. I'm just giving you an example. And then the inland destination to Kansas City, we can go by intermodal rail. We have two options there. We have one option there, intermodal rail, BNSF, and then we have two options by different, and a trucking option, and then we have Norfolk Southern. It's also a rail option. Two rail options, intermodal, and then one truckload option to get to Kansas City. So all of these options for different stages, we can represent them as a network diagram. And this is what's the purpose of this part of the lecture, is to show you how to make a network representation of all your transportation options and then find routes which make sense. So this would be the network representation. We start at Shenzhen, okay, and then we list the cost and the time for each move. So we can go to Yantian port or Hong Kong port. Then from there, we can go to Los Angeles or New York ports. And from there, we have, from New York, we have multiple options to go to Kansas City, truck or rail. And from Los Angeles, it's rail to Kansas City. Okay. So notice that the ports also take time. So the Los Angeles node here is the Los Angeles port, which takes 5 days of processing. New York port takes 3 days. So the Yantian and the Hong Kong ports also take some time. So you could alternatively draw this diagram by saying Shenzhen to Yantian, $35, it takes like 2 hours. So maybe like 0.1 of a day or something. And then put like 2 days at the Yantian port. Or Shenzhen to Hong Kong, you could put like, 0.25 of a day, a quarter of a day to just make that trip. It's not that long, or 2 hours or something. And then put 5 days at the Hong Kong port. So we just kind of combined the port time because of the ship schedule into this moving from Shenzhen to Yantian. But it doesn't take 2 days to go from Shenzhen to Yantian. It's just the time at the port. So an alternative representation would be to make this time from Shenzhen to Yantian very tiny, because it's a very small journey, 0.1 day or something like that, and then move 2 days at the Yantian port or 1.9 days at the Yantian port, and so on for Hong Kong. Okay, and so that's how you can get a network representation. Now, based on this representation, you can find various paths connecting Shenzhen and Kansas City. So if you look at this picture, you can go at the top path, Shenzhen to Yantian to Los Angeles port to Kansas City. That's path 1. Or you'd go the bottom path, Shenzhen to Hong Kong, and then from Hong Kong to Los Angeles, West Coast, and then Los Angeles rail to Kansas City. That's path 2. But you could also go Shenzhen to Hong Kong and then go East Coast to New York, and then go from New York by rail to Kansas City. That's path 3. And that path 4 is Shenzhen to Hong Kong to East Coast or New York port, and then from truck to Kansas City. You have 4 possible paths. So you could find more options and find more paths. I'm just showing you that, whatever options you find, you're going to get a network diagram, something like this. And then you can find the paths. And then you add up the time and money spent along each path to get the total transportation expense and duration for each option. So when we do that for the 4 paths, we get the first path, Yantian to LA to Kansas City, costs $2,235, takes 38 days. The second path costs $2,155, takes 34 days, and so on. The cheapest path is through New York, Hong Kong to New York, and then rail to Kansas City. And it also takes the longest. So this is the trade-off that you have. You can pay a little bit more, cut down the journey time, or you can save some money. And it also will depend on how much volume you're shipping per year, how many containers you need to ship per year. And then you can also use this total transit time as part of your lead time, and then do your inventory calculations to see the impact on inventory cost of which route you pick. Okay. And you could have more than 4 options, right? So you have to work with transportation service providers to list all your options and find the total cost and total days. Now, till this point, we haven't looked at variability in transit time. Ports can have congestion, ships can have accidents, storms, pirates, other issues can cause delays. And so there's a variability in these times. It's not always going to take 38 days. It might take 42 days or 35 days. It's not always going to take 34 days and so on. So the reliability of transportation service has 2 dimensions or phases. There's execution credibility. Does the carrier load all the containers committed, or does it overbook and then leave some containers and for the next ship and you're delayed by a week? Did the carrier stop at all the ports agreed to? Did the carrier reserve capacity on the right vessel? Or did it bump the shipment to a later vessel? So all this is, how good the carrier is to their word. And then the schedule consistency, they quote a schedule, okay, we'll get your shipment to this port on this day. Did they meet that or not? And then you can look at historical data of things shipped with that carrier to kind of look at, okay, do they usually meet what they quote or not? Okay, this was a study done by MIT where they look at, what was the actual transit time versus what was quoted on the contract. And what they found is that usually the actual transit time is more than the contracted transit time. This blue line, the 45-degree line, if the points near the blue line show situations when the actual transit time was exactly equal to the quoted time or almost equal. Points below the blue line is when the actual time was faster. So they quoted 20 days, but got it in 18. Okay. But you can see that very few points are near the blue line or below the blue line. Most points are above the blue line. And then if you put a regression line through the actual data, the red line is the actual regression line, which shows, being above the blue line, that on average, you should expect worse performance than the contracted time. So if they're saying 20 days, you average around 26 days. They take 6 days more. If they're promising 30 days, you average around 33, 34 days. Okay? So the pro tip is to don't go by the contract, but go by the historical performance of the carrier. Okay? So either you use your own data if you've used the carrier in the past, or you collect data about that carrier, how long shipments are actually taking on the route that you are interested in, on that particular route. Because, different ports or different routes can have different efficiencies. And so it depends on the route. It can vary by route. So the route that you are taking, look at historical data and base your expectations on the historical data, not on what they're saying. Now, the same study also looks at, where is the source of variability. So what they show is they look at the coefficient of variation for different stages of some key routes, like Asia to North America, South America to North America, Europe to North America, North America to Europe. Coefficient of variation takes the standard deviation divided by the mean. What it does is kind of standardizes the variability so you can compare options that have different means. Okay, so you can look and see that the ocean transit time is pretty reliable. South America to North America, point to the standard deviation is like 20% of the mean. So if you have 5 days quoted, it's plus minus 1 day, usually. Okay, but for some of the other options, like at the ports, look at the ports, there's a lot of variability. The standard deviation is a large portion of the mean. It's almost equal to the mean. And if you look at the land side transit on both ends, that's also highly variable. Okay, so the ocean transit part is not where the delays happen. The delays happen at the ports or the land side. So let's say we got historical data and then we estimated the variability for different parts of our journey. This is the exact same data, the exact same options, transportation options. All we have done is we have added the standard deviation of the transit time. So Yantian, Shenzhen to Yantian port was taking 2 days. It still takes 2 days on average, but standard deviation is 1 day. So it could take 3 days, could take 1 day. Hong Kong port being very busy, adds a lot of variability, plus standard deviation is 5 days. And so in the red, for each leg of the journey, the standard deviation based on historical data is shown. How would you calculate that? You would get historical data for shipments, you calculate the average, calculate the standard deviation. You can do all that in Excel easily because, for the same 2 points, like Yantian to LA, sometimes shipment would take 20 days, sometimes 18 days, sometimes 25 days. So you'll have this variability in the historical data, and then you can calculate the standard deviation and see what it comes out to be. Now, obviously, it might come out to be like 1.93 days. It doesn't have to be exactly 2 days. But I'm just making up some numbers to represent, to show you how you incorporate that variability in your analysis. You'll have to find the actual data and numbers for the options you're actually considering. So we add the variability to our network diagram. And then what we do is when we go to our 4 options, remember we were adding the money. So we said if you go to Shenzhen to Yantian, it's going to be 2 days plus 20 days, 22 days and time. And so you add the time and the money. And then you go to Los Angeles, that has another 5 days. So 22 plus 5, 27. Then you go from Los Angeles to Kansas City, adds another 11 days. 27 plus 11 gives you 38 days. So that's what we had, 38 days of transit time. Okay, so you add the dollar amounts, you add the average transit time, but you do not add the standard deviations. For the first option, Shenzhen, Yantian, Los Angeles, Kansas City, the standard deviation is not going to be 1 plus 2 plus 3, which is 6 plus 3, 9. Okay, the standard deviation is going to be much less than 9. Why is it 4.8 and not 9? Because you add variances, not the standard deviation. So you convert the standard deviation to a variance. How do we do that? We just square it. Variance by definition is the square of standard deviation. So the variance here will be 1 squared, which is 1. The variance here will be 2 squared, which is 4. Here will be 3 squared, which is 9. So you do 1 plus 4 plus 9. That is 14 plus 9. That is 22. So you get a total variance of 22. Then you square root that variance to get the standard deviation of the whole journey. And the square root of 22 comes out to 4.8, 4.796. So this is the formula. The standard deviation of the total transit time is you add the variances, the squared standard deviations of all the individual components. You sum them up and you take a square root of the whole thing and you get the standard deviation of the total, which is 4.796. Which I've written as 4.8. You should not round off things, keep things with the decimal places and only round off the final answer. But we can do that for each of our journey, each route. And for the 4 different routes, we get 4 different standard deviations. Okay? And so now we have 3 numbers to compare the routes on. We have the amount of money we have to pay. And then we have the transit time, average, and then we have the standard deviation. Okay, so we have to remember that this formula that we're using to add up variances, it assumes that the variability at different stages of our journey is not correlated, is independent, is not connected to each other. So if you're delayed at the LA port or the delays at the LA port do not affect the delays in the next part of the journey. In real life, that may not be true. If you have delay in one part of the journey, that may make delays in the future part more likely because you may miss the schedule of something and things like that. So another option, instead of adding the variances, would be to look at shipments that have gone through that route. At least if you have used that route in the past, or maybe start off with adding variances at this as an estimate, and then once you have some data on your own shipments, along that route, then you can use historical data to estimate the variability of the complete route. Okay, it's usually it's not always possible to find the historical data on all possible routes and figure out the variability. So this can be like an estimate, one way to get close to the true variability by just adding the variances and taking a square root like I've shown here. But if you do have historical data, then you might want to use that and find the standard deviation of the total transit time from historical data and then use that. So what this allows us to do, the standard deviation, it allows us to model risk. So what if we want to know what is the probability that we will get our order, our goods within 40 days? And maybe we want to pick the route with the highest probability of getting the order within 40 days. Deadlines can be important in many businesses. If you have a selling season, a short selling season, or you have a promotion coming up, you want these goods in your warehouses quickly, or maybe you are using this component or raw material in your own production and you have a production schedule. And so, goods arriving on time can be important. So what this variability estimates of the standard deviation allow us to do is to calculate the probability that we'll get the goods in a certain amount of time for each route. So here I've calculated the probability that we'll get the product within 40 days for each route. So route 1, average is 38, standard deviation total is 4.8, which we showed right here on the previous slide on how to get. Okay. Now, based on this mean and standard deviation, I can get the probability of being less than equal to 40 days in one of two ways. One way is I can convert the average and the standard deviation and the threshold of 40 days into a z-score. So I'll do my threshold value 40 minus the average or the mean value, which is 38, divided by the standard deviation, which is 4.8. I'll get a z-score. And then I will use this formula in Excel, equals norm.s.dist, and in brackets the z-value of 0.4167. And this will give me the area under the standard normal distribution up to the z-value of 0.4169, which is the probability that I'm gonna take 40 days or less, so 0.661. The other option is that we skip the step of calculating the z-value because Excel can do that for us. It can calculate the z-value for us. What I do directly is I do equals norm.dist. I skip the s part, which is a standardized value, which needs a z-value. So I don't use the standardized function. I use norm.dist. I pass it the threshold value, which is 40, comma, I pass in the mean or the average, which is 38 for the first route, comma, I pass in the standard deviation, which is 4.8 for the first route. So equal norm.dist, and in parentheses 40, comma, 38, comma, 4.8 would give you 0.661 as well. You should recreate this table in Excel and calculate these probabilities to get some practice so that you're not concerned about how to do it on homework or exams. We do the same thing for all the routes, and we notice that route 1 has the highest probability, 66.1% chance or 0.661 probability of getting the goods to us within 40 days. Okay. Notice that route 1 does not have the smallest average transit time. If you only look at the average transit time, the fastest route is route 2. Okay, but it has a high variability. It had a lot of high standard deviation. And so that affects the probability calculation, and the probability comes a little bit below route 1, is 65.9% or 0.659. Okay. And notice that route 4 is very close to route 1 in terms of the average time taken, 38 versus 39 days, but it has a higher standard deviation, and so its probability is actually quite a bit lower. It's only a 56.6% chance of getting to us within 40 days. So this sort of probability calculation helps us put a numeric value to the risk involved, and that can help us make decisions on time-sensitive shipments. Okay, so just to recap, we covered about the port to inland distribution center or factory or customer warehouse transportation options with transloading from containers into trucks and so forth. We looked at selecting different transportation options which have different transit times and different lot sizes, and seeing how that affects the total cost, inventory cost, and transportation cost. We looked at how to plan for international shipments by finding different options from transportation companies, getting data, making a network diagram, figuring out which route takes the least time or is the least costly. Then we looked at how to deal with risk. Okay, so we looked at how to factor in the variability to talk about risk and probabilities. So this covers a range of types of analysis and transportation decisions that transportation managers, logistic managers take. Please remember that whenever the transit time changes, that means your lead time is changing. And so your safety stock and inventory costs would change. So whenever you're picking transportation decisions, even here, because the average time is different and the standard deviation is different, each of these routes has an implication for your inventory costs. And you can put in these transit time and standard deviations into the inventory cost calculation formulas and figure out the impact it would have on your inventory cost. Now, for routes that are very close, like 39 versus 38 days, and standard deviation is also pretty close, the impact is not going to be very high. Like they're both gonna, the difference in inventory cost is not going to be very high between route 1 and route 4. And so if you do have routes which are very close to each other, you might just say, okay, I'm going to compare route 1 and route 4 on the price, and route 1 is cheaper and go for route 1. But if it's you're going to be using this route a lot, it's very relevant to estimate your inventory cost impact and make a total cost type of decision.